one half of the time step, and then in the remaining part of the step, that is like there are two steps, but it's essentially one time step. In the next step, the missing links are between these two qubits, which were initially not coupled. So it is, I mean, like a minimal model of quantum many-body quantum dynamics, and it kind of mimics the properties or properties which are observed in generic systems. So in this setting, for example, the random quantum circuits allow analytical derivations of a wide range of quantities like entanglement, growth, information scrambling, and also spectral properties like the spectral form factor. But one has to take some special, I mean, in the limit of where the local Hilbert space dimension Q is infinite. And these are a series of works. I know it's an incomplete list, but these are few seminal works in these directions. Now, this model is, I mean, there are, so to speak, the minimal solvable models of many-body quantum chaos, which are solvable, as we will see, and you might already have seen in talks yesterday and today. Whose building block has also two features, but the unitarity one is more sort of special in the sense that it not only satisfies unitarity with respect to the usual temporal direction, but also it generates is unitary along the spatial direction also. So this unitarity with respect to the spatial direction turns out to be crucial and makes these corresponding models to be solvable. And one does not need randomness or unphysical driving in these cases, in the sense that you can couple all neighboring sites with the same dual unitary gate. And for these models, one can construct, one can actually analytically get a spectral form factor which agrees with the random matrix theory, entanglement, growth, correlation functions, OTOCs, so on and so forth. So these are some important works which have explored these different properties. And fortunately, we have seen many of the talks based on these works in this workshop. The building block of these dual unitary models, I'm just having one slide just to set the setting. So is a unitary operator written diagrammatically or diagrammatically in the form of a box with input I alpha is like the input qubits, J beta are the output qubits. In the bipartite notation product basis, written like this, U dagger will be represented by a different color. It's just the complex conjugate of complex conjugate transpose of U. And we define a dual of U. So this operation, I just define it over here because it's going to play a very crucial role later on. So we define a dual of U of bipartite gate with input legs I alpha J beta, where we interchange these two indices, alpha and J. So alpha and J are changed. So we have alpha beta. So I'm using the notation which is used in quantum information theory, where one has Latin and Greek indices for the first and second subsystem, and makes sense also in this context. So now this realignment operation actually groups these two Greek indices over here, ij over here. So this UR takes input now as ij and spits out alpha beta as it is, ij as input and alpha beta as it is output. Okay, now how can I view this UR in terms of the original U? So original U takes I alpha as input, but now this takes ij as input and spits out alpha beta. So it's actually 90-degree rotation of this means we have flipped, so to speak, the role of space and time, which we have seen in this many times in this workshop. So it's just the rules of space and time are flipped under this operation. So it's called dual of U, and in quantum information community is called the realignment operation. And in general, you don't expect under such a reshuffling or realignment operation to remain unitary. And just I want to say that there is a related operation of partial transpose where you actually one interchanges indices corresponding to either first subsystem or second subsystem. For example, this rearrangement we are going to see later in the talk also. So I define it over here where we interchange, we actually do transpose in the second subsystem. So we interchange alpha and beta. So this will be denoted by subscript 2 just to avoid confusion with the usual partial with the usual transpose. And U is called a dual unitary if UR is also unitary. So if U is called a dual unitary if it remains unitary under the temporal direction and also along the spatial direction. And these are the building blocks of these what calls, so to speak, the solvable models of quantum chaos. Since we are going to see the role of entanglement measures, these local unitary invariants and all. So in fact, Carol did a very nice job yesterday by introducing all these measures. So just for completeness, I'll just have a slide on this for these quantities in order to, I mean, just to see the convention, because different conventions are used. So I just, but the essential idea was already given by Carol yesterday. So the idea is like this: if I take any bipartite unitary gate, I apply it on a product state. In general, it's going to create an entangler state. And now we look at the linear entropy of this reduced density matrix. So we take linear entropy because it's just a polynomial in row 1. It's just a trace row 1, that's just 1, and trace source 5. We just take 2 moments for simplicity. And taking this as a measure of entanglement, now we take an ensemble average of these product states. So imposing taking, for example, a uniform measure like Haar measure, and this entangling power of U is determined by the entangle operator, and by E of U is the operator entanglement of U and operator entanglement of US. And so shown by Paolo Zanardi around 2000. So it is quite remarkable that this entangling power of this, where we have on the left hand side we have actually state property, and the right hand side we have operator property. So it's determined by the operator entanglements of E of U and E of US. And entangling power in our convention, so it is different from the seminal work of Zanardi. So he uses different convention, but we'll use EP to be normalized between 0 to 1. Now, so far so good, but if I take, for example, identity and swap gate, which we yesterday say swap is like in this workshop, we also saw that swap is like an very non-local gate. But identity and swap, for example, both have entangling power equal to 1. So entangling power does not distinguish between two gates U and US, which are very, I mean, have very different non-local content. So in order to avoid this sort of problem, or we can say one more quantity was defined, which is called gate typicality in this work, which takes into account, which kind of separates, distinguishes two operators U and US. And it turns out this EPGT projection is like, I mean, it will be like our phase space, so to speak. So as a phase space for these operators. So how does, and this plot was also shown yesterday by Carol, but I'll slightly add some of the things over here. So projection of unitary group on this EPGT plane, so is like this. So EP can be 0 to 1, GT is also 0 to 1. So within the square, only this light shaded blue color is the allowed region of allowed region for unitary operators, means there will be no unitary operators in the white part. And you can see the dual unitaries from swap to DC naught line. This is the dual unitary line. Then there is T dual line. First thing to note is that this EPGT plane has a perfect symmetry around GT equal to half line. So if there is a gate, for example, over on this T dual line, so these are operators for which partial transpose is unitary. If I multiply by swap, I'm going to over here. So any gate U, if I multiply by swap, I'm going to reflect around GT equal to half line. So this is going to be crucial for the constructions of dual unitary operators. Okay, now this dual unitary operators are building blocks of, so to speak, these solvable models of many-body quantum chaos. How about this T-dual? So we saw first talk in the first session where these diagonal weakly diagonal interactions with on-site disorder was discussed. So those are like, I can think of those as T-dual unitaries because their partial transpose will be unitary. And yeah, that's diagonal interactions, but weakly diagonal, so they will be closed identity. And also this recently introduced strongly localized models, which Bruno was talking yesterday. So in stock, the smaller value of G's in this terminology will be smaller power of entangling power. So over here, one would expect. By the way, can you see my cursor, Ranjan?
Yes,
yes,
okay.
We can.
Thanks. Thank you very much. So in this terminology, those gates will be gates with small entangling power over here, very close to zero. And there is one more fantastic result about qubits, 2-qubit case, which is that the lower boundary, this boundary, is given by the fractional powers of swap, which was shown in this work. This actually provides the boundary of the possible gates for 2-qubit gates, and this boundary is not known for higher dimensions. And since and these gates are actually used in many body contexts also. For example, in the characterization of isotropic XX model. This is a paper by Tomasz, I think 2018 paper. Yeah. And yesterday we also saw in many body contexts, one writes these in terms of these R of lambda is like identity plus I lambda divided by 1 plus I lambda. This is just to ensure unitarity. So the reason for writing these operators like this is because it is one can interpret this as acting on two sides, that it exchanges this situs with probability amplitude, which is proportional to lambda. But that's the only reason. And we saw in Peter's talk a nice this recent work by Google, where they have taken square root of swap gate. So square root of swap will correspond to lambda equal to 1 in this case, which we saw in Peter's talk also. So I'm just kind of relating how these different sort of these boundaries which appear on the 2-qubit case are used in different many body contexts in different settings and all. And this for 2-qubit case, how about for D greater than 3 or sorry, I apologize. Yeah.
So here the alpha and lambda are any direct connected?
No. You see, S power 1 will be swap, but lambda tends to infinity will be swap. Lambda tends to infinity will be swap because swap definitely exchanges.
Okay.
So
okay.
Just looking at this, but the idea is the same. So for Q greater than 2, this first there is T-dual line, there is dual unitary line, and there is, by the way, I should emphasize that in the 2-qubit case, there are no gates with entangling power greater than 2/3. It's a well-known fact in quantum information theory, which is actually going to have impact on the dynamics of dual unitaries. For example, when these 2-qubit gates are used as building blocks of the models, it's going to have effect on the dynamics also. So, but for Q greater than 3, there are gates actually, apart from Q equal to 3, there is a gap on this dual line, which is still an open problem, which our other colleagues have also found independently. But the general situation is like this: there is a continuous line between swap and 2 unitary. The important point is this point, which is a common intersection of this dual unitary line and T-dual line. So on this point, the unitary remains unitary under partial transpose as well as realignment, or you can think that U is maximally entangled operator, and it remains maximally entangled if I multiply by the non-local gate like S. So for example, if I just multiply a gate like over here, if I multiply by S, it becomes U times S, that will be maximally entangling. Entangling power does not change, but gate typicality changes. Okay. Now this maximum, I just include this slide because this two unitary thing is, it appears in different contexts and has been given different names by different communities. So entangling power is equal to 1 if and only if if we have a unitary operator, it remains unitary under realignment and puncture transpose. So it's we usually call it two unitary, which was introduced by Carroll's group some time ago. We use usually this, and it's a maximally entangling because on the average it creates maximum entanglement when applied on an ensemble of product states. And it's called the maximally scrambling also in some contexts, like for example this paper by Yoshida and Presco and others. So it's called maximally scrambling unitary also. And tensor which can be constructed from this two unitary, or the other way around, the two unitary which is constructed from this perfect tensor is a perfect tensor in the sense that under arbitrary partition we can define an isometry. Let me just give an example of a two unitary written in terms of. So this is an example of a two unitary, what's called I mean, it's a permutation matrix, and the corresponding state which it gives is what's called a minimal support army state. What I mean to say is that it's a particular kind of two unitary. Not every two unitary can be written like this. So it is a controller NOT gate between 1 and 2, and then you run the controller NOT in the other direction. So it is a Clifford C0. Okay, so these are adders in opposite directions for which the Clifford is written here. It turns out that this can be shown is two unitary or maximally scrambling or maximally entangling for all odd dimensions. For even dimensions, it is dual, but it's not maximally entangling. Now we come to I mean, we'll mix the things in the sense that what role do they play. So I'll just recapitulate what was said in earlier talks also. So in the dual unitary models, there is there's unitarity in the temporal direction, which I mean, there's a causal structure that outside the light cone the correlation will be 0. Now there is spatial evolution which will pose that I mean, under this causal structure, the correlations outside this this light cone will be 0, and inside will be non-zero. Now under the dual unitary evolution, these correlations can survive only on the light cone. And the corresponding this, so to speak, the building blocks, the whole beauty of these models is that, as we have heard also from other speakers, that the whole I mean, the fate of the correlations is decided by a two-qubit channel, or in general will be a Q square by Q square matrix, so to speak. And those these channels, so pictorially it looks like this. If we take the Liouville superopera representation of these of the dual unitary model constructed out of U, so it is given by this, and you see the role of these operations which we defined T2 and R1. So R1 is actually the what R I was saying. So I have to differentiate between two rearrangements are possible. So we're writing R1 and R2, but this M plus of U crucially depends on partial transpose and realignment. So the whole this fate of the correlations will be determined by the spectra of these matrices M plus minus. Okay, so now the problem reduces to first these channels are proven to be, these are contractive, and their spectra lies within the unit disk. They're unital, so that means there is a trivial eigenvalue corresponding to the vectorized identity. So we will order these eigenvalues. Lambda 0 is just a trivial eigenvalue, and then lambda 1 up to lambda q square. So these are the ordered eigenvalues of this M plus channel. And there was So this is the first paper which actually found these non-vanishing correlations on the light cone, and based on the eigenvalues of this these channels, an ergodic hierarchy was proposed, like for example, non-interacting, non-ergodic, ergodic and mixing, ergodic and non-mixing, ergodic and mixing, depending on the eigenvalues of these channels. And we added in our recent work the Bernoulli circuits, for which all these lambda these eigenvalues vanish, non-trivial eigenvalues vanish. So the corresponding these m plus minus channels are actually completely erasure or depolarizing channels, as we will say. So these are like, this will be at the apex of this ergodic hierarchy. Now, what's the setting? So what we do is we take dual unitary gate and add locals or on-site disorder like this. So we have a unitary operator U, we sandwich it between locals, U1 tensor U2, V1 tensor V2. So under locals, the operator entanglement E of U does not change because it is a local unitary invariant to the entangling power of U prime and U are same, because these are local unitary invariants, and also dual unitarity is preserved. So under dual unitarity, it is dual unitarity, of course, will be preserved under local by adding root local fields or disorder. But the the eigenvalues, the spectra of m plus of U prime and m plus of U will be different, as was discussed in this paper of Peter and Austin Lemacraft. The spectrum of m plus of U prime and m plus of U will be different. Let's see some examples. Q equal to 3, we take 4 different dual unitary operators and look at the spectra of m plus. The largest eigenvalue, that's lambda 1, and lambda q square minus 1 will be, which will be lambda 8 in this case. And look at the spectra of this m plus and m. This is essentially m plus channel. So the first case is close to EP equal to 1, and then we turn on, so to speak, the interaction. We increase the entangling power and go from left to right, and you can see that this ring actually, for some of these, apart from these, I mean, nice shapes and all that, one thing to observe is that it kind of shrinks. Okay, this spectra. So there seems to be some correlation with the entangling power. And what we found is something like this. This is a rudimentary phase diagram. So the correlation with the entangling power is for qubits, because the qubit world is different than q greater than 2. And it actually is rooted in the APGT plane plot, which I showed, which didn't have gates beyond 2/3. So there is a nice, I mean, very important value of entangling power given for given local Hilbert space dimension q, given by q square minus 2 divided by q square minus 1, which turns out to be 2/3 for qubits. So one can get non-mixing behavior, mixing behavior for 2 qubit case. For q greater than 2, for swap, I mean, all the eigenvalues are equal to 1. If one multiplies by these locals, you can at least get non-mixing behavior. And sometimes the correlations won't, they will just oscillate, but on the average average will be 0. And there is this value EP star. Up here one can get mixing, but beyond this, if I take dual unitary gates which have entangling power greater than this EP star, EP star is given by this, as I was saying. Beyond this EP star, the corresponding circuit is guaranteed to be mixing. So this is the crucial observation which result which we found, and I'll try to justify this rudimentary phase diagram in the next part of my talk. Okay, so given the spectrum of this channels, so to quantify the decay of correlations and all, so we define the spectral gap as spectral gap usually is defined by 1 minus lambda 1 and the corresponding mixing rate. So this is in open system dynamics usually we call the relaxation rates and all. So we define the rates as minus log of the modulus of the of the corresponding eigenvalue. So mu0 will be just mu0 will be just 0 corresponding to the trivial eigenvalue. And we define these rates because, as I was saying, the spectrum of under the multiplication by locals, the spectrum changes. So we have to take some kind of either the maximum over some set, or take some average with respect to some R. So we define these quantities which should be local unitary invariant. So we define mu plus of u by taking the average over mu1, by taking maximum over mu1, and mu plus of u will take average over mu1 of u prime essentially, and take average over the single qubit unitaries. So how does it look for the qubit case? Turns out to be a bit easier, because for 2 qubit case, nu plus of u turns out to be for a particular subset of taking a particular subset of these single qubit unitaries. One can show that this nu plus of u is given by 1 minus EP by EP max. So EP max is the maximum entangling power possible for qubits, which is 2 by 3. So you can see that nu plus is determined by EP, and similarly mu plus depends on EP. And it should not be surprising that entangling power actually it only depends on entangling power, because for qubit is the class of dual unitary operators is just a one parameter family. But the fact that it is a monotonic function, as is shown over in this plot, the fact that it is a monotonic this function is a non-trivial result, but is just a one-to-one. I mean, it's just depends on the entangling power. So this is for the q equal to for the two qubit case. How about for q greater than 2? So q greater than 2, we just separate out from this channel the trivial eigenvalue, where this is the maximally entangled. So we just take out the maximally entangled, separate this projector corresponding to the eigenvector corresponding to the trivial eigenvalue, and do some hard averaging. Hard average over the single qubit unitaries, and find the average of mod lambda 1. So mod lambda 1 was, is, and this approximation is given by square root of 1 minus EP, and is shown numerically over here also. So what one sees is, first important thing to note is that the qubit case just separates out from the rest of this, as we were seeing in these EPGT projections also. But for other cases, what we see some sort of collapse happening for different dimensions. So if I take a gate with entangling power over here, so qubit case is different, but over here for different dimensions, the average of mod lambda 1 is kind of, I mean, it's not exactly same, but it is same to some accuracy. So this is sort of universal behavior of this average of mod lambda 1. Now, if I take the average of, for example, some second or third largest eigenvalue, we don't expect it to be correlated to entangling power like this, because out of, I mean, the unitary group has some q square minus 1 parameters. We don't expect a single number like entangling power to decide the whole fate of the correlations, but because it is a special class of unitary operators, the dual unitary operators, in this case, in some sense, to some accurate, I mean, to some order, it crucially depends on entangling power, and it's given by square root of 1 minus EP, and it gets, this approximation gets better and better as entangling power tends towards 1, which is shown in this plot for q equal to 4. Now, q equal to 3, as I was saying, q equal to 3, the dual line is not continuous. In the sense, you cannot find entangling power greater than some numerical bound we have from 0.94 or something. 0.94 to 1, there are no two unitary operators apart from q equal to 1. So that's why we have done it for q equal to 4 over here. And does entangling power tell us the whole story? No. First, if I take a particular ensemble of, I mean, we have taken some special class of dual unitary operators. These diagonal constructions, we will see later in the presentation how these are constructed, and see how they are correlated with the entangling power. And we have mu plus is like the average thing. It is sort of related, one-to-one correlated with entangling power, but nu plus, which is maximization over mu1, has actually a spread. So entangling power does not sort of uniquely defines this rate, the maximum over this mu1. So nu plus does not depend on just EP, but there will be some other invariants on which it will depend. And so far as we know, there are no other invariants to characterize dual unitaries apart from the entangling power or operator entanglement of EUS, because operator entanglement of EU is maximum, is just maximum operator entanglement. Okay. So now we give some, so the bound I was saying, this entangling power beyond EP star, the circuit, the corresponding dual unitary circuit is guaranteed to be mixing. So this results from this simple calculation. First, so we take m plus tilde by subtracting this trivial eigenvalue and take the norm square of this, and it turns out that the norm square of this is proportional to 1 minus EP, and it's a local unitary invariant. Okay, now norm square of these are the eigenvalues of this m plus tilde. So they are upper bounded by q square minus 1 into 1 minus EP. Now, if I replace all these by the smallest possible eigenvalue, so this will be certainly bounded above by q square minus 1 into 1 minus EP, because this is bounded by this. So one can just show that this modulus of q square minus 1, that is the smallest non-trivial eigenvalue, is upper bounded by 1 minus EP of u. Now, EP of u can have value from 0 to 1. So if I have EP equal to this EP of u equal to 0, we can have lambda 1 to be less than or equal to 1. We can have equal to 1 also, because EP of u is 0, that will correspond to the swap gate. And if EP of u is 1, that is for the this two unitary case, lambda 1 is equal to 0 in that case. So it cannot be less than 0, so it is equal to 0 in that case, and it's going to play a role. So for EP greater than 0, one can always add these random locals to make at least one mode will be decaying, and it will correspond to the mixing mode. And one can actually define a hierarchy in terms of entangling powers. Okay, one can define hierarchy in terms of entangling powers for which one is guaranteed to get q square minus k modes if the entangling power is given by this. So if an entangling power is greater than 1 minus k divided by q square minus 1, then you are guaranteed these q square minus k modes will be less than 1, and the q square minus k modes will decay, which is shown in this picture. Up to here, lambda q square minus 1 is less than 1. Up to here, q square minus 2 is less than 1, and there's a hierarchy. Now you see the special this EP star. So EP star corresponds to k equal to 1. If I put k equal to 1 over here, so we will get EP star is q square minus 2 by q square minus 1. Now, if lambda 1 is less than 1, since it is the largest non-trivial eigenvalue and it's less than 1, the others are all less than 1. So in these cases, the circuit is the corresponding circuit is guaranteed to be mixing. All the modes will decay instantaneously. And how one can justify this result is that when EP star is greater than EP, the interactions between these citrices are very strong, in the sense that no local tuning of the parameter, no local tuning of these fields can localize or decay or prevent these correlations from decaying. And as I actually forgot this thing to emphasize. Yeah. So there is mixing, and at the end there is this the one which we introduced, the Bernoulli circuits. And the Bernoulli circuits, as was shown over here, also correspond to dual unitary operators which are two unitary. So you actually make the dual unitary brick wall construction using these two unitaries. The corresponding circuit will be Bernoulli, which we will see over here, and it is easy to see, because in this case m plus of sigma, I mean, is pictorially given by this, and it reduces to just a completely depolarizing channel. Why? Because in this case, UT2 dagger is just identity. Okay, so you just realignment of identity is just this projector, which is by 5 plus is just the generalized Bell state. Okay, so all lambda k's in this case, just rank 1. So all lambda k's in this non-trivial eigenvalues in this case vanish. So this is really at the apex in the sense that all these rates which I was defining mu plus of k, they are actually, apart from the trivial eigenvalue, which is always there, all the non-trivial eigenvalues, eigenmodes actually decay instantaneously, and there are infinite rates corresponding to this. So lambda k is equal to 0 for all k greater than 0. So all modes decay instantaneously. And in fact, what we showed is that in these cases, owing to the property that it's not only unitary with respect to this sideways contraction, one can contract in legs like this, the partial transpose. Owing to the partial transpose, one can show that extended observables also decay instantaneously, which we have explained it in our paper. And
excuse me, Suhail. Yeah, sorry. I mean, probably you have around 3 minutes, 3-4 minutes. Just,
okay. I think I'll be done by.
Okay. Thanks.
So now, as I was saying, this entangling power in the rudimentary phase diagram which I showed. So entangling power plays a very crucial role in whether deciding the circuit will be mixing and all that. And if it is equal to 1, then the correlations will decay instantaneously and all. So it certainly plays a, if not the solely role, but it plays a predominant role in describing the dynamics. Now is how to construct these dual unitaries across this EP equal to from 0 to 1 for d greater than 2, for example, how to construct these dual unitary operators, because first thing to, as actually this point was emphasized in many of the talks yesterday as well as today. There's no known parameterization apart from the 2-qubit case. So in the 2-qubit case, a general this dual unitary gate can be written in terms of this V of j, where this is pi by 4, and j, and is essentially the XXZ trotterized integrable chain. So pi by 4, and j, and then you have these SU2 gates in between. And in this case, the entangling power depends on just j. So there's just one parameter line, and this parameterization exhausts all possibilities for dual unitaries. Now, if the same set of, same kind of parameterization as yesterday Peter and Tomasz was saying, if same kind of this construction is applied for q greater than 2, one indeed gets one can indeed construct dual unitary operators. So first thing is, any unitary which is of the form V times S is essentially unitary. If V has a property that it is T dual, that it remains unitary with respect to partial transpose, then under the multiplication by swap, it is T dual. It's dual unit. It becomes dual unitary, and it is easy to see in the EPGT projection, because if you are on this T dual line under multiplication by swap, you just get on the top of this dual line, and one can actually not only have this if he is T dual. So these are, I have written over here also, these are easy to construct in the sense that T dual is with respect to partial transpose. The easier family to see is the just diagonal phases. Just you put the phase. In fact, this one is also D times S, as we have explained it in our paper. This is just D times S, and more general will be block diagonal constructions. So one can not only think in terms of uniform blocks, one can think a particular, not all block diagonals will give you dual unitary. A particular class of these block diagonals will give these dual unitaries. But the limitation with this method is on this EP line from 0 to 1, the maximum EP you can get is EP star, and for this 2-qubit case, EP star is the maximum possible. So we don't have any problem with the qubits, but for q greater than 2, EP star, there are gates between EP star and 1 which are not covered in this construction. And I mean, there's some works which are in preparation. So what we first thought is, why only take swap times diagonal? Why not take a dual unitary permutation? And you can easily construct them as we have explained it in the paper. Also, there's a particular combinatorial structure which is underlying these dual unitary permutations. By the way, as yesterday Carol was also emphasizing, two unitaries have a structure, I mean, have a combinatorial structure of orthogonal Latin squares. These will have semi-Latin, because these are not much constrained than two unitaries. They have sort of semi-Latin, orthogonal semi-Latin structure. So if I take any permutation matrix which is dual, not only swap is one possibility, but some other also, and multiply it by a diagonal, you can actually go beyond this construction. I mean, one can construct gates which are entangling power greater than this EP star also. And in the given paper, as was nicely described, this based on couplet cat maps, also there is a construction we have also given, and we heard from Boris's talk also. And in last year we wrote a PRL which in which we defined nonlinear maps on this space of bipartite unitary operators for whose attracting fixed points are these dual unitaries. So for arbitrary dimension in some, so these they have the beauty that if you give a proper initial condition to these maps or dynamical systems, proper initial conditions, they will actually they actually are guaranteed to converge with probability 1 to dual unitaries, ranging from swap up to EP equal to 1. Okay, and even I mean, we think that these maps are in some sense the only way to explore gates. For example, this is an easier way, I would say. This is an easier way to explore gates between EP star and EP by giving initial conditions which have entangling power greater, larger entangling power, and then evolve under these maps. So, and there have been other constructions also in this Thomas Goose group based on complex Hadamard-based constructions. Let me just summarize. So we just showed that entangling power of the building block of the two unitary plays a crucial role in understanding this ergodic hierarchy. So there is a universal behavior for locally averaged spectral gap for Q greater than 2, Q equal to 2 is a different word. And we also constructed Bernoulli circuits, which are at the apex of an quantum ergodic hierarchy, in the sense that the correlations decay instantaneously and the rates are infinite. And some of the directions in which we are looking are non-dual circuits on this EPGT plane. Right now, these are dual unitaries. These are like the maximally chaotic models. And there are some smaller entangling powers, as we saw today also and yesterday's talks. One can construct some localizer or strongly localizer models. So we are also looking at, for example, a special line is there, which also leads to, which is sort of alternate route to reach two unitary. Is this where E of U is equal to EUS? That's like the GT equal to half line. This line also has, how about if one takes these as the building blocks of these two unit building blocks of these lattice models? What are are there some simplifications and all? So these are some of the directions in which we are working. And also for some other reasons also, we're interested not only in many body contexts, but also these maximally entangled or dual unitary operators in unequal dimensions for finite circuits with times greater than L by 2, and also multipartite or multi-unitary matrices in the sense that you don't assume unitarity with respect to 2, but more than 2 directions of the space or whatever the time direction you have. Okay, thank you very much for your attention.
Thanks, Suhail. Thanks for a nice talk. So probably we have time for 1-2 quick questions. Any question from the audience? Okay, so I have a very naive question. So I just wanted to know that is there any microscopic model one can think of, and we can see this mixing and the crossover from mixing and Bernoulli's type of phases? Because I mean, of course, all these things are in the context of unitary, but is there a known local microscopic Hamiltonian? I mean, sorry.
Well, as I was saying, this is, for example, this one is
Right.
the factorization of XXZ, this chain. This one, for this only for qubits that you have this sort of integrable as well as this. This is only true for qubits, but
Right.
But not for q greater than 2. So this can be sort of viewed as a trotterization of this, and also this transition we heard in John Chalker's talk today also. So there was this weak diagonal model with weakly coupled sites with online with on-site these fields. So
Right.
he actually talked about the q greater than infinity. But for me, the interesting thing was also, if you look at q equal to 2, that's the smallest possible dimension. In fact, in that case, for all the epsilon he was talking about, for all orders of epsilon, you always have this localized phase. And when you go for q equal to 3, you can actually have both this localized as well as ergodic phase also. Something like what we had,
Yeah, Suhail.
Okay.
Yeah, Ranjan, I think
Yeah.
for Q at least greater than 2, that is starts from 3. As of now, we don't know a Hamiltonian model
Okay.
from mixing, going from mixing to Bernoulli.
Okay.
Okay.
I think,
So,
Arvind, we can discuss it later because we are kind
yeah,
of running
Sure.
out of time. So thanks, Sohail. We can talk later.
Yeah,
Okay.
sure.
So now the next speaker is Daniel. So is he here?
Yes.